Hey everyone, and welcome. Today, we're going to break down one of the most fundamental concepts in all of computer science, semaphores. You can think of them as these invisible traffic cops, or silent gatekeepers, that basically prevent our entire digital world from crashing down into total chaos. Seriously, just think about it for a second. Your computer is probably doing hundreds, maybe thousands of things right now. So how does it stop, say, two different programs from trying to print a document at the exact same time, or from writing over the exact same piece of memory? That is the core problem we are going to unpack today. So this all comes down to an idea called a critical section. It's just a piece of code that needs to access some kind of shared resource. Could be a file, could be a printer, whatever. And just like a changing room at a store, only one process can be inside its critical section at any given time. If a process is in there, any other process that shows up just has to wait its turn. Simple as that. Okay, so here's what we're going to cover. First, we'll dig into this critical section problem. Then, we'll introduce the very first semaphore as a potential solution. After that, we'll uncover a really big flaw in that initial design and then build a much smarter system to fix it. And finally, we'll look at some of the hidden dangers that come with using such a powerful tool. All right, let's dive right in. The whole goal here is pretty straightforward. We need to set up some rules so that all these different processes can cooperate without stepping on each other's toes. We need a system that makes sure when one process is using a shared resource, like that printer we talked about, no other process can just barge in and interfere. So how do we actually manage this? Well, we need a gatekeeper. We need some kind of mechanism for a process to request entry, let's just call that wait, and then a way for it to announce that it's leaving, we'll call that signal. This whole entry and exit protocol is what keeps that critical section safe. And that brings us to the first real solution to this problem, which was actually invented decades ago, the semaphore. It's a really elegant and powerful idea that acts as our perfect little gatekeeper. At its heart, a semaphore is surprisingly simple. It's really just an integer, a number. The magic isn't the number itself, but in how we're allowed to interact with it. We can only touch this integer using two special indivisible operations, wait and signal. And that word atomic, or indivisible, is key. It just means the whole operation happens all at once, with absolutely no chance of being interrupted partway through. Okay, so let's actually look at the code for this. The semaphore, which we're calling S here, it starts with a value of 1. That basically means available. Now, when a process calls the wait function, it hits this loop that checks if S is 0 or less. If S is 1, it just sails past the loop and immediately subtracts 1, making S 0. And that's like locking the door. Then, once the process is all done, it calls signal, which just adds 1 back to S, making it 1 again, and unlocking the door for whoever's next. And here's what that looks like in practice. You have your critical section, and you just wrap it. Before you go in, you call wait on the semaphore, which you'll often see called a mutex. That's short for mutual exclusion. If you get the lock, you go in, do your thing, and once you're finished, you call signal to release the lock. It's a pretty simple and pretty effective wrapper. But, and this is a big but, this really simple solution has a massive hidden flaw. While it totally works, it is incredibly inefficient. It basically creates a busy gatekeeper that never gets a break, and that causes a really big problem. So think about it. What happens when a process calls wait and the resource is already locked? Well, with this simple design, the process gets totally stuck in that while loop, just hammering the CPU, asking over and over and over again. Is it free yet? How about now? Is it free now? This is what we call busy waiting, or a spin lock, because the process just spins in place, doing nothing useful. And this is a huge problem. It's like a kid on a long car ride, endlessly asking, are we there yet? Are we there yet? It doesn't make the car go any faster, it just wastes energy and annoys everyone. All those CPU cycles being burned by the spinning process could have been used by another program to do some actual productive work. So, obviously we need to fix this. We need a much smarter system. Instead of having our waiting process just spin around frantically, what if we could just put it to sleep? And you can really see the difference here. On the one hand, you have busy waiting, where the process is stuck in that loop, wasting precious CPU time. But then you have the much smarter system, blocking. In this model, the process is just put into a waiting queue, kind of like getting in line at a store, and the operating system suspends it. It's put to sleep. This frees up the CPU to go do other things, which is way more efficient. Now, the code gets a little more complex, but the idea behind it is actually super elegant. If you look at the new wait function, you can see that if the resource is busy, the process gets added to a waiting list, and then this block function is called, which is what puts it to sleep. Then, when the other process is done and calls signal, it pulls a process from that waiting list and calls wake up to bring it back to life. No more spinning, no more wasted cycles. So we've got a much better system now. But semaphores are kind of like chainsaws. I mean, they're incredibly powerful and effective tools, for sure. But if you use them incorrectly, you can cause some really serious system-wide damage. And there are 3 classic ways things can go horribly wrong. You can have a deadlock, you can have starvation, or you could accidentally break the very mutual exclusion you were trying to protect in the first place. First up is deadlock. This is a real classic. It's a kind of deadly embrace where 2 or more processes just grind to a halt because each one is waiting for a resource that the other one is holding. Nobody can move, it's a complete standstill. And this traffic gridlock is just a perfect way to picture the problem. Look at the code. Process 0 grabs semaphore S, and then it tries to grab Q. But at the exact same time, process 1 grabs Q and then tries to grab S. What's the result? The traffic jam you see right there. Each process is holding one intersection and waiting for the other one to clear. The entire system is just frozen. Okay, the next danger is starvation. This one's a little more subtle. It's a situation where a process isn't technically deadlocked, but it just never gets picked from the waiting queue. It's ready to go, it's waiting patiently, but it just keeps getting overlooked again and again. This image really drives the point home. Imagine that big truck is a really long, complex job. If the system's scheduler is set up to always prioritize smaller, quicker jobs, the little cars, that big truck might end up waiting forever. It's effectively starved of the CPU time it needs to finally get its work done. So what's the big takeaway here? Well, the power of semaphores comes with a huge amount of responsibility. A single misplaced wait call or a forgotten signal can create bugs that are incredibly hard to track down, and they can cause deadlocks or starvation that bring an entire system to its knees. You know, semaphores absolutely solved that original critical section problem, but their fragility, the fact that a simple programming error can be so catastrophic, it really pushed computer scientists to search for even better tools. And that leads to a really fascinating question. If a simple number and 2 little functions are this risky, what might a safer, more robust gatekeeper actually look like?